slower, but earlier. Harvard Mark I failed very rarely. 6. In the end, tube-based CPUs became dominant because the significant speed advantages afforded generally outweighed the reliability problems. Most of these early synchronous CPUs ran at low clock rates compared to modern microelectronic designs. Clock signal frequencies ranging from 100 kHz to 4 Ms were very common at this time, limited largely by the speed of the switching devices they were built with. 27. Transistor CPUs. IBM PowerPC 604E processor. The design complexity of CPUs increased as various technologies facilitated building smaller and more reliable electronic devices. The first such improvement came with the advent of the transistor. Transistorized CPUs during the 1950s and 1960s no longer had to be built out of bulky, unreliable and fragile switching elements like vacuum tubes and relays. 28. With this improvement, more complex and reliable CPUs were built onto one or several printed circuit boards containing discrete, individual components. In 1964, IBM introduced its IBM System /360 computer architecture that was used in a series of computers capable of running the same programs with different speed and performance. 29. This was significant at a time when most electronic computers were incompatible with one another, event hosts made by the same manufacturer. To facilitate this improvement, IBM used the concept of a microprogram, often called microcode, which still sees widespread usage in modern CPUs. 30. The System /360 architecture was so popular that it dominated the mainframe computer market for decades and left a legacy that is still continued by similar modern computers like the IBM Z series. 31. 32. In 1965, Digital Equipment Corporation, December, introduced another influential computer aimed at the scientific and research markets, the PDP-8. 33. Fujitsu board with SPARC 6480X processors. Transistor-based computers had several distinct advantages over the predecessors. Aside from facilitating increased reliability and lower power consumption, transistors also allowed CPUs to operate at much higher speeds because of the short switching time of a transistor in comparison to a tube or relay. 34. The increased reliability and dramatically increased speed of the switching elements, which were almost exclusively transistors by this time. CPU clock rates in the tens of megahertz were easily obtained during this period. 35. Additionally, while discrete transistor and IC CPUs were in heavy usage, new high-performance designs like single instruction, multiple data, SIMD, vector processors began to appear. 36. These early experimental designs later gave rise to the era of specialized supercomputers like those made by Cray Inc. and Fujitsu Limited. 36. Small-scale integration CPUs. CPU, core memory and external BIS interface of a December PDP-8/I, made of medium-scale integrated circuits during this period. A method of manufacturing many interconnected transistors in a compact space was developed. The integrated circuit, IC, allowed a large number of transistors to be manufactured on a single semiconductor-based die, or chip. At first, only very basic non-specialized digital circuits such as NOR gates were miniaturized into ICs. 37. CPUs based on these building block ICs are generally referred to as small-scale integration, SSI, devices. SSI ICs, such as the ones used in the Apollo guidance computer, usually contained up to a few dozen transistors. To build an entire CPU out of SSI ICs required thousands of individual chips, but still consumed much less space and power than earlier discrete transistor designs. 38. IBM System /370, follow-on to the System/360, used SSIX rather than solid logic technology discrete transistor modules. 39, 40. December's PDP-8/I and KI-10 PDP-10 also switched from the individual transistors used by the PDP-8 and PDP-10 to SSICS. 41, and their extremely popular PDP-11 line was originally built with SSICS but was eventually implemented with LSI components once this became practical. Large-scale integration CPUs. Lee Boyce published influential articles, including a 1967 manifesto, which described how to build the equivalent of a 32-bit mainframe computer from a relatively small number of large-scale integration circuits, LSI. 42, 43. The only way to build LSI chips, which are chips with 100 or more gates, was to build them using a metal oxide semiconductor, MOS, semiconductor manufacturing process, either PMOS logic, MOS logic, or CMOS logic. However, some companies continued to build processors out of bipolar transistor logic, TTL, chips because bipolar junction transistors were faster than MOS chips up until the 1970s. A few companies such as Datapoint continued to build processors out of TTL chips until the early 1980s. 43. In the 1960s, MOS ICs were slower and initially considered useful only in applications that required low power. 44, 45. Following the development of silicon gate MOS technology by Federico Faginat, Fairchild Semiconductor in 1968, MOS ICs largely replaced bipolar TTL as their standard chip technology in the early 1970s. 46. As the microelectronic technology advanced, an increasing number of transistors were placed on ICs, decreasing the number of individual ICs needed for a complete CPU. MSI and LSI ICs increased transistor counts to hundreds, and then thousands. By 1968, the number of ICs required to build a complete CPU had been reduced to 24 ICs of 8 different types, with each IC containing roughly 1000 MOSFETs. 47, in stark contrast with its SSI and MSI predecessors. The first LSI implementation of the PDP-11 contained a CPU composed of only 4 LSI integrated circuits. 48, microprocessors. Die of an Intel 80486DX2 microprocessor, actual size, 12.6.75mm, in its packaging Intel Core i5 CPU on a VAIO E-Series laptop motherboard, on the right beneath the heat pipe. Since microprocessors were first introduced, they have almost completely overtaken all other central processing unit implementation methods. The first commercially available microprocessor, made in 1971, was the Intel 4004, and the first widely used microprocessor, made in 1974, was the Intel 8080. Mainframe and mini-computer manufacturers of the time launched proprietary IC development programs to upgrade their older computer architectures, and eventually produced instruction set compatible microprocessors that were backward compatible with the older hardware and software. Combined with the advent and eventual success of the ubiquitous personal computer, the term CPU is now applied almost exclusively, to microprocessors. Several CPUs, denoted cores, can be combined in a single processing chip. 49. Previous generations of CPUs were implemented as discrete components and numerous small integrated circuits, ICs, on one or more circuit boards. 50. Microprocessors, on the other hand, are manufactured on a very small number of ICs, usually just on. 51. The overall smaller CPU size, as a result of being implemented on a single die, means faster switching time because of physical factors like decreased gate parasitic capacitance. 52-53. This has allowed synchronous microprocessors to have clock rates ranging from tens of megahertz to several gigahertz. Additionally, the ability to construct exceedingly small transistors on an IC has increased the complexity and number of transistors in a single CPU manifold. This widely observed trend is described by Moore's law, which had proven to be a fairly accurate predictor of the growth of CPU and other IC complexity until 2016. 54-55. While the complexity, size, construction and general form of CPUs have changed enormously since 1950-56, the basic design and function has not changed much at all. Almost all common CPUs today can be very accurately described as von Neumann stored program machines. 57b. As Moore's law no longer holds, concerns have arisen about the limits of integrated circuit transistor technology. Extreme miniaturization of electronic gates is causing the effects of phenomena like electromigration and subthreshold leakage to become much more significant. 59-60. These newer concerns are among the many factors causing researchers to investigate new methods of computing such as the quantum computer, as well as to expand the usage of parallelism and other methods that extend the usefulness of the classical von Neumann model. Operation. Inside of a laptop, with the CPU moved from socket, the fundamental operation of most CPUs, regardless of their physical form they take, is to execute a sequence of stored instructions that is called a program. The instructions to be executed are kept in some kind of computer memory. Nearly all CPUs follow the fetch, decode and execute steps in their operation, which are collectively known as the instruction cycle. After the execution of an instruction, the entire process repeats with the next instruction cycle, normally fetching the next in-sequence instruction because of the incremented value in the program counter. If a jump instruction was executed, the program counter will be modified to contain the address of the instruction that was jumped to, and program execution continues normally. In more complex CPUs, multiple instructions can be fetched, decoded and executed simultaneously. This section describes what is generally referred to as the classic RISC pipeline, which is quite common among the simple CPUs used in many electronic devices, often called microcontrollers. It largely ignores the important role of CPU cache, and therefore the access stage of the pipeline. Some instructions manipulate the program counter rather than producing result data directly. Such instructions are generally called jumps and facilitate program behavior like loops. Conditional program execution, through the use of a conditional jump, and existence of functions. C. In some processors, some weather instructions change the state of bits in a flags register. These flags can be used to influence how a program behaves, since they often indicate the outcome of various operations. For example, in such processors, a compare instruction evaluates two values and sets or clears bits in the flags register to indicate which one is greater or whether they are equal. One of these flags could then be used by a later jump instruction to determine program flow. Fetch. Fetch involves retrieving an instruction, which is represented by a number or sequence of numbers, from program memory. The instruction's location, address, in program memory is determined by the program counter, PC, called the instruction pointer in Intel x86 microprocessors, which stores a number that identifies the address of the next instruction to be fetched. After an instruction is fetched, the PC is incremented by the length of the instruction so that it will contain the address of the next instruction in the sequence. D. Often, the instruction to be fetched must be retrieved from relatively slow memory, causing the CPU to stall while waiting for the instruction to be returned. This issue is largely addressed in modern processors by caches and pipeline architectures. See below. Decode. The instruction that the CPU fetches from memory determines what the CPU will do. In the decode step performed by binary decoder circuitry known as the instruction decoder, the instruction is converted into signals that control other parts of the CPU. The way in which the instruction is interpreted is defined by the CPU's instruction set architecture, ISA. Often, one group of bits, that is, a field, within the instruction, called the opcode, indicates which operation is to be performed, while the remaining fields usually provide supplemental information required for the operation, such as the operands. Those operands may be specified as a constant value, called an immediate value, or as the location of a value that may be a processor register or a memory address, as determined by some addressing mode. In some CPU designs, the instruction decoder is implemented as a hardwired, unchangeable binary decoder circuit. In others, a microprogram is used to translate instructions into sets of CPU configuration signals that are reapplied sequentially over multiple clock pulses. In some cases, the memory that stores the microprogram is rewritable, making it possible to change the way in which the CPU decodes instructions. Execute. After the fetch and decode steps, the execute step is performed. Depending on the CPU architecture, this may consist of a single action or a sequence of actions. During each action, control signals electrically enable or disable various parts of the CPU so they can perform all or part of the desired operation. The action is then completed, typically in response to a clock pulse. Very often the results are written to an internal CPU register for quick access by subsequent instructions. In other cases, results may be written to slower, but less expensive and higher capacity main memory. For example, if an addition instruction is to be executed, registers containing operands, numbers to be summed, are activated, as are the parts of the arithmetic logic unit, ALU, that perform addition. When the clock pulse occurs, the operands flow from the source registers into the ALU, and the sum appears at its output. On subsequent clock pulses, other components are enabled and disabled to move the output, the sum of the operation, to storage, for example, a register or memory. If the resulting sum is too large, i.e., it is larger than the ALU's output word size, an arithmetic overflow flag will be set, influencing the next operation. Structure and implementation. Block diagram of a basic uniprocessor CPU computer. Black lines indicate data flow, whereas red lines indicate control flow. Arrows indicate flow directions. Hardwired into a CPU's circuitry is a set of basic operations it can perform, called an instruction set. Such operations may involve, for example, adding or subtracting two numbers, comparing two numbers, or jumping to a different part of a program. Each instruction is represented by a unique recombination of bits, known as the machine language opcode. While processing an instruction, the CPU decodes the opcode, via a binary decoder, into control signals which orchestrate the behavior of the CPU. A complete machine language instruction consists of an opcode and, in many cases, additional bits that specify arguments for the operation, for example, the numbers to be summed in the case of an addition operation. Going up the complexity scale, a machine language program is a collection of machine language instructions that the CPU executes. The actual mathematical operation for each instruction is performed by a combinational logic circuit within the CPU's processor known as the arithmetic logic unit or ALU. In general, a CPU executes an instruction by fetching it from memory, using its ALU to perform an operation, and then storing the result to memory. Beside the instructions for integer mathematics and logic operations, Various other machine instructions exist, such as those for loading data from memory and storing it back, branching operations, and mathematical operations on floating point numbers performed by the CPU's floating point unit, FPU. 61. Control unit. The control unit, CU, is a component of the CPU that directs the operation of the processor. It tells the computer's memory, arithmetic and logic unit and input and output devices how to respond to the instructions that have been sent to the processor. It directs the operation of the other units by providing timing and control signals. Most computer resources are managed by the CU. It directs the flow of data between the CPU and the other devices. John von Neumann included the control unit as part of the von Neumann architecture. In modern computer designs, the control unit is typically an internal part of the CPU with its overall role and operation unchanged since its introduction. 62. Arithmetic logic unit. Symbolic representation of an ALU and its input and output signals. The arithmetic logic unit, ALU, is a digital circuit within the processor that performs integer arithmetic and bitwise logic operations. The inputs to the ALU are fed data words to be operated on, called operands, status information from previous operations, and a code from the control unit indicating which operation to perform. Depending on the instruction being executed, the operands may come from internal CPU registers, external memory, or constants generated by the ALU itself. When all input signals have settled and propagated through the ALU circuitry, the result of the performed operation appears at the ALU's outputs. The result consists of both a data word, which may be stored in a register or memory, and status information that is typically stored in a special, internal CPU register reserved for this purpose. Address generation unit. Address generation unit, AGU, sometimes also called address computation unit, ACU. 63, is an executime unit inside the CPU that calculates addresses used by the CPU to access main memory. By having address calculations handled by separate circuitry that operates in parallel with the rest of the CPU, the number of CPU cycles required for executing various machine instructions can be reduced, bringing performance improvements. While performing various operations, CPUs need to calculate memory addresses required for fetching data from the memory. For example, in-memory positions of array elements must be calculated before the CPU can fetch the data from actual memory locations. Those address generation calculations involve different integer arithmetic operations, such as addition, subtraction, modulo operations, or bit shifts. Often calculating a memory address involves more than one general-purpose machine instruction, which do not necessarily decode and execute quickly. By incorporating an AGU into a CPU design, together with introducing specialized instructions that use the AGU, various address generation calculations can be offloaded from the rest of the CPU, and can often be executed quickly in a single CPU cycle. Capabilities of an AGU depend on a particular CPU and its architecture. Thus, some AGUs implement and expose more address calculation operations, while some also include more advanced specialized instructions that can operate on multiple operands at a time. Some CPU architectures include multipleggers, so more than one address calculation operation can be executed simultaneously, which brings further performance improvements due to the superscalar nature of advanced CPU designs. For example, Intel incorporates multiple AGUs into its Sunday Bridge and Haswell microarchitectures, which increase bandwidth of the CPU memory subsystem by allowing multiple memory access instructions to be executed in parallel. Memory Management Unit, MMU. Many microprocessors, in smartphones and desktop, laptop, server computers, have a memory management unit, translating logical addresses into physical RAM addresses, providing memory protection and paging abilities, useful for virtual memory. Simpler processors, especially microcontrollers, usually include an MMU.cache. A CPU cache, 64, is a hardware cache used by the Central Processing Unit, CPU, of a computer to reduce average cost, time or energy, to access data from the main memory. A cache is a smaller, faster memory, closer to a processor core, which stores copies of the data from frequently used main memory locations. Most CPUs have different independent caches, including instruction and data caches, where their data cache is usually organized as a hierarchy of more cache levels, L1, L2, L3, L4, etc. All modern, fast, CPUs, with few specialized exceptions, 65, have multiple levels of